First speaker today is going to be Glenn Washer. He is the professor of civil and environmental engineering at the University of Missouri-Columbia. Today he's going to be presenting on the implementation strategies for risk-based inspection. So everyone, welcome Glenn.
It was originally given in July. And so this is an update on a pooled fund that Missouri's currently leading. And so it's not really a conclusive or the results of the study. It's more like what we're doing and an update on the progress. We've got 8 states across the country that are working in this project to look at the risk-based inspection procedures that were originally developed under a previous NCHRP project. And so this is kind of just an update on what's going on in that area, and I'll talk a little bit about the method in case it's not something that's familiar to you. NCHRP 1282 was a project that looked at reliability-based bridge inspection practices. At the time, that was the term used. They're risk-based inspection practices, and were originally modeled on practices used in some other industries like the petroleum and chemical and processing industries. It was published back in 2014 in NCHRP report 782. I was working with Rob Connor over at Purdue at the time, and some folks from CTL and some other folks on the team there on the reliability-based bridge inspection practices. And the idea was to try to develop a procedure that all the states could implement in order to get inspection practices that better met the needs. And so the idea is to try to find ways that you can identify those bridges that are low in risk and could have potentially a longer inspection interval, and those ones with elevated levels of risk where you'd want to inspect them more often. And the existing 48-month policy that Federal Highways had 7 factors in it, which are they're kind of risk factors. Some of them are maybe not the ones we choose today, but the ones they chose back in the 80s when they did that. 100-foot span length is one of them, certain ADT, and had to be in condition rating 6 or better. And so there were 7 parameters. Not that many states used it. I think when we started the study back in whenever it was for the 782, there was only around 15 states that were using it at all. Most states were using it for culverts, that 48-month policy. More states have started using the 48-month policy since the time we did this research. We'd like to think we encouraged some of that. But looking forward, there was a memo sent a couple of years ago by Shea Burrows, and that allowed you to use this process that we developed in the research, which is an expert elicitation process, essentially, in order to identify bridges for the 48-month interval. So you wouldn't necessarily have to use their 7 parameters. You could have different parameters. The main problematic one that people seem to find was the span length being limited to 100 feet. But anyway, you could modify that if you did this procedure. And so the research really was, a large part of the research was really developing a process by which people could go through and in order to identify those attributes of a bridge that made it more reliable or less reliable, and build a sort of a risk model, if you will, that was relatively easy to implement. Now, since the time of the research, of course, states have gotten a lot more involved in asset management and bridge management software and deterioration modeling and all these things. The original RBI concept, which was largely based on expert elicitation, provides a framework which you can put lots of quantitative data in if you have it. But we were trying to build one which, if you didn't have it, you could use it, thinking, well, if the framework was there, then as the quantitative data came on, and I'll talk a little bit about that towards the end of this presentation, you'd be able to use that. In the revisions to the National Bridge Inspection Standards includes risk-based inspection. Those are out now. I don't know when they'll come back. They were sent out for comment, and they got lots of comments, and they're finishing the final rules now. I've not got any insight into when, it could be this afternoon or it could be a year from today. I have no idea when it's going to be. We are trying to finish this pooled fund beforehand so that states could use the results in the when that becomes available to them, when they could possibly have inspection intervals as long as 72 months. The basic concept, and I think people in this group have gotten a lot more familiar with risk now than they were maybe before, but the basic concept is to say, well, what can go wrong with my bridge? And through doing that, identify damage modes for elements and what are the deterioration mechanisms that are at work, corrosion, fatigue, or otherwise, and try to figure out a way to estimate how likely it is for any given bridge based on the reliability characteristics, or what we'd call attributes of the bridge. And an attribute would be something that contributed to its durability or lack of durability. So concrete cover might be one, whether epoxy-coated rebar is used might be one. Other factors that you've noticed in your state could be part of it, like ADT. And those attributes are identified through an expert elicitation process that is described in the report using something called a reliability assessment panel wrap panel, which is some folks with experience from the state and expertise in different areas, a structural engineer, inspection program manager, probably a materials engineer, people that would have a background in history and what the designs are in that state and where design problems have been in the past. And they have past experience. And this is modeled after things done in other industries where, you know, if you're in manufacturing, for example, and you want to do performance-based maintenance on your machines, what do? You ask the people to operate the machines, which are the ones that give you problems and which are the ones that don't, right? Because they're the ones that know, and they know about the specific environment in which that's operating. So, you know, bridges in Arizona probably have different attributes than bridges in, say, Pennsylvania, because the environment's entirely different. And then the second part of that is what are the consequences? And so it's kind of a semi-quantitative methodology. You're scoring a bridge basically based on its attributes and what the consequences might be if there was severe damage or at some point, and trying to place it on a risk matrix. And so, you know, some of the language surrounding this is kind of a sign of the times, which was when the research was done not long after the accident in Minneapolis. And so, for example, when we originally did the research, you know, risk was not something we wanted to talk about in the same sentence with bridges. So it was a reliability-based inspection practice, even though the original problem statement said it was risk-based. And so that sort of turned around in the 10 years since that's happened, or 15 years, so that now we can talk about risk, so now we're back to calling it risk. And so we have something called an occurrence factor, which is how likely it is that it's really a probability of failure, but you didn't want to say probability of failure. So you have to define what that means. In our case, we define it as deteriorating to a condition rating of 3, not necessarily falling down, but it becomes, you know, loses its serviceability. Base that on attributes of a bridge, and that's a relative estimate based on certain characteristics of the bridges. And the report listed a lot of common attributes and suggestions for criteria of how you might score them. One of the things we're looking at in our research is variations to that, okay? We're looking at, is there different attributes that ought to be included? What is the commonality of 6 or 7 states do the same analysis of the same type of bridge? They end up with the same list of damage modes and the same list of attributes and even the same criteria, or do they vary? And so we wanted to study that, and that's what we're doing in this process. And the ultimate goal is to try to develop a handbook that all states could use in order to implement this technology. As I mentioned before, the original plan was, or the original scope is to just use a simple risk matrix that's 4 by 4. And so things that tend towards the upper right corner would get shorter inspection intervals. Ones that were down in the left corner that had low risk if there was damage, if it did deteriorate to a condition rating of 3, and unlikely that it would happen in the next 6-year interval, which is sort of the period of performance that we've identified in this research for that. You could have a 72-month interval if you were way down in the low and remote range. These would be bridges that were in good condition, probably young, and had good durability attributes like epoxy-coated rebar, plenty of concrete cover, maybe even sealing on the deck. And it envisions inspection intervals of up to 72 months, which would be new for NBI. And so what we're doing in the pooled fund is trying to study this process. We've got these 8 states, 6 of them we've done analysis with already on certain types of bridges. I think I'll show a table in a second. Certain families of bridges to look at their attributes. Look at, are the damage modes they identified the same? You would think they would be, but it's good to test that. How much variation is there between those attributes? Is there a rationale for maybe a standard set of damage mode and attributes that would sort of shorten the process so you didn't have to start by figuring out what the damage modes were? And also we're looking at, is there quantitative data available that could support that occurrence factor / probability of failure in the future? Now, I put this construction zone here because all this is sort of work in progress. So like I mentioned, this project's ongoing. It's not really close to the conclusion yet, but I'll tell you what we've been doing. So we held RAP meeting in 6 states, and then there was a pandemic. So this has been a year where we didn't get that much progress. 4 states were originally in the pooled fund, 2 that joined. Since then, 2 additional have joined. We've got planning underway to do additional RAP panels. And as I mentioned before, this is a panel of people from the state that are familiar with the operational environment of that state and can speak to what sort of past experiences they had with design issues and identify problems they might have, and sort of customize the risk model to their particular state. We collected data on primary damage modes. We sort of organized in that. One of the challenges we faced was, every state has different words for the same thing, and so you've got to try to reduce that data down afterwards and get commonality in what these attributes actually mean. The process sort of looks like this flow chart. You identify damage modes, and for bridge decks you might have just a couple. What we found is that, delaminations and spalling is obviously the big one, and then Cracking also sometimes comes up. But so you've got this damage mode of what the inspector is actually going to see, and then you identify what attributes contribute to that. And this is only part of the list, but some part of it, let's say age, how many spalls and patches there already are, that might speak to the element condition rating for that particular structure. What kind of reinforcement type does it have? Then we've got some criteria, and we're assigning point scales to that. And so that's like a lot like a model consultants probably generate every day on different types of things, just according to what their characteristics are. Do these wrap panels, and the wrap panel is kind of a voting process. It's meant to try to get an objective analysis to sort of neutralize people, take out some of the group dynamics, and have a discussion about what they are. So we start out with, okay, tell us, if someone came into your office and said that steel bridge is condition rating 3, what do you think the reason it's a condition rating 3 is? And you get answers like impact damage. Well, if it's a steel bridge, you get impact damage and you get corrosion, right? Those are the primary reasons. And so then you're going to use that as a damage mode and take off and identify what attributes are for that. So we've done in the study steel structures and pre-stressed bridge structures. Those are the primary families of bridges that we're looking at, and trying to look at what the damage modes are for those. Section loss and corrosion, fatigue, cracking, and impact are what's typical for steel. Pre-stressed, delamination and spalling, impact damage, exposed strands, and cracking, and substructures are usually always delaminations. You look at what the attributes are that contribute to those. Again, those are characteristics like durability characteristics. Does it have epoxy-coated rebar? Are we sealing it? Things like that. And we rank those in order to come up with a scoring process. And we do see a lot of commonality, like in deck. We've done 6 states, and all 6 states pick as their top attributes. Well, how much salt do we put on it? What's the traffic? Interesting, average daily traffic. We've been doing some studies in Missouri, and in Missouri we found that didn't really correlate with deck condition, but that's usually one that's identified by them. What is the current condition of the deck, and what's the rebar type? Those are identified by everybody, and then other states have some other attributes, and the attribute list gets kind of long because you get some sort of odd ones in there, here and there, but the basic ones are pretty common, we found in this study, which is one of the things we're trying to figure out in the study. Same with steel corrosion damage. What are the main ones? Well, salt application. What is the coating condition, and what is the joint type? And as you know, I don't have to tell this group, the joint types comes up all the time. So we're looking at those attributes that the states have identified, looking at which ones are already in the manual that was the original 782 report, and what ones we need to add. And also looking at how common these are. If we look across all of these risk models, the ones for pre-stressed superstructures, decks, and substructures, and for steel superstructures, decks, and substructures, are the ones that appear more often than others. And of course the current condition obviously is one that, right, if you ask how likely is it, if you ask somebody, how likely is it that that particular deck is going to be a condition rating 3 in the next 6 years, for example? Well, the first question they want to know is what's the condition now, because if it's a condition rating 4 now, that's a lot different answer than if it's a condition rating 7. So it makes sense that would be among the most common attributes. Salt application obviously is another one, and joint condition. Those are sort of the top 3. Current condition of the bridge, joint condition, and level of salt application. What we're doing in the research now is we've got these models for the 6 states and going through, looking at the criteria for the different attributes they've identified, and we're doing something called backcasting, we're doing backcasting to take a sample of bridges, like 10 bridges in a state, and go back through their history and look at, if we started back in the 90s doing a risk-based inspection, would that have had a negative impact? Was it at some point something that happened that you would have missed if you've been doing, say, a 6-year interval? And so we sort of take the risk model and go back, and one of the problems with these sort of risk models predicting the future is you have to wait for the future to happen to know if it worked or not. So the only other option of that is to say, okay, put myself back in time. If I go back to 96 and I were to implement this idea of risk-based inspection, would it have had a negative impact? Would it have been that something missed? And so that's kind of what we're working on now. Also trying to link the criteria to data sources so that the states can just pull from the data that they already have in the element level, in the condition ratings or otherwise. So we put all this together, the damage modes, the attributes, and criteria. They form a risk model for the state that they can apply to a particular bridge or to families of bridges to set these and characterize what are the parameters of ones that are going to get longer inspection intervals, what are the parameters for ones that are going to get shorter inspection intervals. Then the second half of that equation, really I think maybe the harder one, is the consequence factors. What are the consequences if this became in condition rating 3, given its characteristics of, is it redundant, is it heavy traffic area, is it a remote bridge, is it over another roadway, et cetera. And so we're currently working on that and some improved models for that based on some NBI data. And other sort of things that are ongoing in the research. One was, I mentioned before that condition rating is one of the primary attributes that people want to know in this risk model. And so are the condition ratings consistent through all the states? And so we went and got inspection manuals from 47 states to look at, how do they define the condition ratings? Because actually the way the MBI was set up originally, the states are encouraged to have their own criteria for these. And you find that the criteria are pretty similar in most cases. We found the most variation was in condition rating 6 for percent deterioration of bridge decks, where actually it varies quite a bit. Some states might have a qualitative thing like minor, and there's a list here that's highlighted. That's what I wanted the pointer for. Like one state says it's minor, another state's up to 10%, another state's 10 to 20%, another state has a criteria of up to 20%, another state doesn't have any definition at all. And so there's a fair amount of variation in that. We found that in most cases there's not that much variation. Either they don't have a criteria or the criteria are not that different, say 2 and 5%. In a few select cases, if you were just base the whole thing on, say, condition rating 6 at bridge decks, that would not be uniform for different states, assuming that they followed their own manual when they did the MBI condition ratings. So the other things that are being sort of studied either inside or outside of the research is how to have quantitative occurrence factors so you don't rely so heavily on the expert panel, or at least back up the expert panel. Look at things like time and condition ratings or time and state, as some folks would say, for different inventories of bridges. And looking at the hazard function, which is a sort of complicated statistical thing you can get out of it, which you can convert into a probability of failure, which would only take you an hour or two to explain to somebody. As long as you have an hour or two, I guess that's not a problem. But, it gets complicated. It's on the next slide here. These hazard functions show the change in hazard over time, and this is an example just from Kaplan-Meier survival analysis of NBI data in Missouri, and this is on cast-in-place decks. And so you can produce this hazard, and it tells you what the likelihood of transition is cumulatively into each year. You can convert that into a probability of failure value if you want. Now, that is a more quantitative way to do it, but in order to get up enough data to be able to make that kind of a model and have it be statistically significant, you have to take really a lot of mean data or average data. So for any particular bridge, that might not apply. So I think you don't really get away from the attributes entirely. You still would have to look at whether the bridge has other characteristics that indicate it's going to perform well or poorly in the future. And this is just another slide, similar type of information, right? That as we develop more and better deterioration models, the framework of risk-based inspection is set to be able to accept that kind of a thing. And even we've looked at some other data in other studies that for these things that are attributes, can we study what their actual impact is? And so, for example, this is a hazard, what's called a hazard ratio, which would take another hour to explain, but for salt application in Missouri in different districts, and it essentially tells you that the risk is about twice for every 1 ton more of salt you put on your roadway based on historical data in Missouri. Or the second one shown here is on average about 10% increase in risk for every 10 years older you are when you enter a condition rating. And so those type of data, they'll be developing in the future. The people don't really have them now, but they will in the future. So as I mentioned, backcasting is going on. We're also looking at, rather than using a matrix, maybe using a numbering line, which gives you a little more flexibility. It might be more practical for longer term implementation. So that's sort of the nature of the work. As I mentioned, this is kind of an update. This is what was going on in the project. We're going to be developing a handbook that people can use once we get towards the end of this study. In there will also be attributes for non-redundant members, which is an adaptation of an old study that Texas and several other states worked on to look at modifying inspection intervals. Now, that wouldn't be allowed currently under the NBIS, but maybe someday it will be, to change that in-depth inspection interval for non-redundant members. That'd be for potential for future use. Okay, and that was about all I had.
Thank you very much, Glenn.
Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.